Kia ora, and good morning, everyone. Welcome to our first speaker presentation session at day 2 of the Research Software Engineer Aotearoa New Zealand conference. I hope you enjoyed yesterday, and in our session today we have 3 speakers, and we will be looking at different tools showcase. So all 3 speakers will be talking about different tools and workflows that they assembled. Our first speaker today is Simon Anastasiadis from Social Wellbeing Agency. And Simon will be talking about accelerating data wrangling, a researcher-built dataset assembly tool. Over to you, Simon.
Kia ora koutou. Thank you for the introduction. Let me start with the problem or the need for this tool. So I'm an Integrated Data Infrastructure Researcher, or IDI. This is a collection of data sets from across New Zealand government that have been collected together by Stats New Zealand and linked. So while I cannot see who a person is, I can see where the same person turns up in multiple government data sets. And that allows for research to consider a much richer picture of who a person is and what's going on for them. It does, however, bring with it some significant challenges. There are in the environment more than 400 source tables. And even if I only use 10% of that for a single analysis, I need some education information, some health information, some tax information, some benefit information. It's still a lot of different sources to try and pull together into a standard data set in order to run analyses or to deliver research results. Especially challenging given that all of those source tables are in very different formats, essentially whatever format the originating agency possesses. And you can hopefully easily imagine, as you increase the number of data sets, the number of different pieces of information you want, the complexity of this problem to kind of simply get a data set ready for analysis increases. My solution to this has been to build a dataset assembly tool. And this does several things for me. It results in a standard process for data preparation, so that can be ingested by the tool. And it reduces the complexity for me as a researcher for assembly down to run the tool. I've experienced significant gains from using the tool. I think the very first IDI project I was involved in, there were 3 staff and it took us at least 4 weeks to do all the data wrangling. Whereas in contrast, the most recent piece of work, I could do that solo in a single week as a result of having access to the tool and associated resources. While I suspect not many of my audience are going to be IDI researchers kind of directly or immediately using the tool, hopefully there's something in this talk to kind of guide your own refinement of your practice, or aspects of how I built the tool that will inform tools you build for yourself in the future. I'm quite pleased with the performance of the tool. Give you a sense of how it's run. This is kind of the largest assembly I ran, output more than 1 billion values, and it took 4 hours. And I realized 4 hours might seem like a long time for some contexts. In the IDI, where that's a shared environment, 4 hours is not an unreasonable time. Perhaps worth highlighting that that's a panel data set. So a single cross-section, which tends to be much more standard for IDI research, can be done in 20 minutes. At that speed, you can iterate multiple times a day. And one of my first uses of the tool, in collaboration with some colleagues, we did iterate 4 or 5 times a day, where they're checking the assembled data. Oh, this isn't quite right, Simon, please fix this. I fix it, reassemble, and 20 minutes later they're using and working with a revised data set. This, the dataset assembly tool isn't the first attempt to simplify research process in the IDI. And prior to building my tool, I did look at other options. Kind of Unfortunately, none of them are quite well suited for what I was looking for. Perhaps these ideas can be split roughly into simplicity of use and simplicity of problem solving if something goes wrong, and separation of kind of purpose. Some of the tools I had encountered previously had bound or included what you were analyzing with the assembly process, which means when you wanted to change what you were analyzing, you had to go into code and make significant edits. I'd also seen kind of parts where the only way to kind of debug is potentially go through 10,000 lines of code and figure out, okay, at what point did the whole thing fail? Neither of which was particularly appealing. So part of my goal in building the tool was to separate out the different pieces that kind of you might want to change separately. And that gives you more flexibility to change them, and then greater ease to, if something's failed, you can just go to the piece that's failed rather than having to search through the entire kind of library or project's worth of code. How does the tool work? The tool works, if you see on the right, we've got several layers of process. Starting with the resource data, the researcher develops and the measures they want to use. Highest qualification, I need to go to the source data and create something that tells me the highest qualification before I assemble it. Information from your population and your events is written into a pair of Excel control files. And then the assembly tool reads the control functions to fetch the population and measures to produce a rectangular table for output. I'm using what I call a who in what pattern of assembly. I think of it as I've got a population and a start and end date. I'm between these dates, and then I've got events, which I've got. And then between those, I'm right. Between those, I'm looking then for the intersection where those people have the same events. The population control file is Excel, so you don't need to, as a researcher, know the language that the tool's written in. All researchers, I think I safely assume, are familiar with Excel. And what goes in here is very much kind of, okay, look in this table, get this column, use these dates. The measure control file, very similar, but tends to be longer. There's usually only one or two populations, but there might be many different measures. What we've done so far has been 560 individual measures. This file's particularly useful because it becomes the starting point for my data dictionary. I can, from that far right-hand column where I've got a notes row description, I can see this is kind of the measure I was intending to build. And if it ever comes to kind of auditing or checking the lineage of my data, I can, via this file, very quickly go, I was trying to build this. It came from this input table, and using that far left-hand column, which contains the file, I can find the file where I built the input source. So as a tool for audit, as a tool for keeping track of kind of data information, this has got multiple uses. What's it doing under the hood? At its core is this query on the right. I won't take you through it. It's a piece of SQL. The essence of the process is that, so the tool's written in R. R kind of plucks the key pieces out of the control file, inserts them into this query, and then runs the query, pushes the query to SQL to be run. And so it's all the kind of the data processing is done in a language that's well suited to data processing, and the kind of the control or the management of it done in a language that's well suited for that type of task. This query outputs a long, thin table. It's just the format easiest to kind of append additional data onto, and at the end it's pivoted to produce a nice rectangular table that a researcher prefers to work from. Things that make the tool effective. Firstly, before any assembly gets executed, all the inputs are validated. I wanted the tool to fail as early as possible with as little delay for the researcher as possible. So if we can detect anything that might cause a failure later on, we stop execution so that it can be fixed beforehand. And mostly that includes things like, do your control files make sense? Are they pointing to valid database objects? I began with an earlier example with 1 billion data points assembled. I realized for some applications that's not a huge amount. But if I've got a 4-hour wait time to run the thing end to end, I might want a faster option. So part of my practice now includes a control for what I've termed development mode, where at a single point I can turn off or turn on limiting output to a subset. And this avoids the hazard of going through and commenting out or having to uncomment all the different filter lines because there's a single point. And when I can turn it on, I have a much sped up process which lets me validate what's happened. And then I can ask for production mode and run it for the desired output. I think I've already touched on this previously. My control file becomes the point for both data lineage and data dictionary. And as a reference for kind of coming back to a project, what did I do? How did I do it? Yes, this becomes a central piece of knowledge. I spoke early on about iterating over with a colleague. Perhaps the ideal workflow or the ideal data flow is linear. Everything starts with raw data and ends up with analyzed results. But as a researcher, my workflow is not linear. I iterate through that middle point, needing some additional prepared information, analyzing it, perhaps modifying it, and previous attempts or perhaps bespoke processes in this space end up with kind of some things get assembled, we realize something else is needed and we assemble it, we realize another thing's needed and we assemble it. And then if you make a change to it, you've potentially got cascades of failures because different ordering, things have dependencies that aren't clear. So by having assembly at a single step, having the tool be fast enough to rerun, I've kind of removed a whole bunch of that stress and complication from delivering projects. And my workflow increasingly looks like what's on the right, where I can be in the middle of a piece of work, I identify a need for something new, pause, find it, build it, assemble it in, and carry on. As an IDI researcher, I'm part of a wider research community, and given the 400-something tables and all sorts of different structure, it can require significant expertise or experience to kind of actually just figure out how should I define the thing that I want to define. Ideally, I'd go to education staff and get qualification definitions from them, and I'd go to IRD staff and get income definitions from them, and I go to MSD staff and get benefit definitions from them. Okay, that's not always possible, but at the very least, if when I build a thing, whether it's highest qualification or receipt of benefit, it can be reused, it can be componentized and kind of shared or circulated or reviewed by an expert without having to see all the rest of the project code, then I've got a gain there. And then beyond that, those individual components have value outside the project. And indeed, I'm already in the process of building a library, both for accelerating my own work and for benefiting researchers to come after me based on kind of these components. For those who are interested, here's where you can find out more. On SWA's website, we have a range of publications, including training videos, and on our GitHub page, there's both the code for the tool and the library of definitions I've been building. Even if using the tool isn't something that's likely to be of use to you, may I recommend the A4 overview or the primer, which captures some of the principles or thinking underlying the tool, which might be useful if you're in the situation of needing to build something like this yourself. Thank you for your time and your attention. I hope you find this beneficial for improving your own practice.
Great. Thank you very much for your presentation, Simon. We have several questions in our Q&A. So Plummer is asking, is there a reason for using a proprietary format, Excel, over comma-separated value, tab-separated value, or similar?
So the tool will read CSV or Excel input. I guess Excel seems to be the thing that most people have and naturally double click on to open in such a file. There's no problem with you using an open office calculator or whatever you prefer to edit CSVs in. The tool will read CSVs just as comfortably.
Great, thanks. And another question from Nick Spencer. Does your pipeline archive each ARD version, or do you just rerun a particular configuration? And what if the base data changes? What do you do then?
So some of that is, at least in the IDI, is controlled outside my hands by Statistics New Zealand. So yes, there's definitely extensions to this in research environments that you've got full control over. But in the IDI, data is kind of versioned every 3 months, what we call a refresh. So the underlying data can't change on you because you point yourself at a specific refresh. And we've got some storage limits because it's a shared environment. So in general, we're overwriting the previous assembly, or maybe you've got 2 assemblies and you leapfrog one over the other, simply because you can't afford, so I guess maybe Stats can't afford to allow every researcher to accumulate gigabytes upon gigabytes of archived analyses.
Mm-hmm. Thank you. And we still have a little bit more time. So there is one more question from Jean Sudlenkov. How difficult was it to get access to the databases owned by different agencies?
So this is more a question related to the integrated data infrastructure. Statistics New Zealand have extensive information about this on their website. They've got a very clear, this is for research only, and an application process for interested researchers. You fill out a form, generally you meet with them to discuss what your research project is. And then there's a series of trainings in terms of ensuring confidentiality is upheld for the data, given that it is unit record. Kind of one of the additional protections for the IDI is that information that comes out of it, say for research reports, is sufficiently protected that we can't re-identify individuals. So only summary information comes out. If you wanted to know more, access to microdata is the team at Statistics New Zealand who can administrate and update the IDI and their website. If you just search integrated data or IDI for Stats New Zealand's website, you should get all the pages that tell you more.
Thank you very much. Yeah, and it's also great to see you you're sharing your work through tools like GitHub, which are one of the most popular places to look for and share also scientific workflows. So I'm really happy to see that and happy that you do that. Thanks once again for your presentation. And as we're moving on to our next speaker, I just want to remind everyone that questions can be asked through the Q&A. You have a button on your right-hand side that says live Q&A, and you can type in your questions there, and then we take these questions to our presenters. And so we're going to move on to our next speaker. Mike Laverick, Hamish Campbell from Coordinates, who's going to be talking about data version control and collaboration for reproducible science with Kart. Over to you, Hamish.
Thank you very much. And I just wanted to add, I'd love to answer lots of questions at the end rather than talking about what I know, because we've already had a few people mentioning data version control, and so it'll be interesting to hear more. My name's Hamish. I'm not an academic. I am a product manager and software engineer for Coordinates.com. Some of you have probably heard of us. We are the New Zealand-based company that powers the LINS data service, the Stats Data Finder. We work with Manaaki Whenua to power their LRIS portal, and Ministry for the Environment. And for over 10 years, we've been a key part of the geospatial data infrastructure in New Zealand. We push out on the order of 100 terabytes of geospatial data of one form or another a year to engineers and planners and scientists throughout the country who are working with data. So we're really interested in the key questions of how you get data to people who really need to use it to do valuable things. My background's in software engineering. I used to work in a GIS team at an engineering company, and that was always a key problem for us. And so that's the sort of the space that I'm coming from. Today I'm talking about an open source project that we have been working on called Kart. I don't really need to probably remind this audience of what reproducibility and replicability means. But in the software engineering world, the idea of being able to have a reproducible build based from your sources is a really important topic. And so there are similar problems that we have. So, how can I duplicate the result using the particular source data or software that I have, and how can I rerun the entire process with new sources? And that fundamentally comes down to three different pieces. One piece is your code, so the stuff that you're writing, your model, your thing that you're running. You have the environments, that's your operating system, all the software libraries that you're consuming, and there's the data, and that's not just the import data, so all the source data that you're consuming that other people might have produced or perhaps you've collected in the field, but also the result data sets that you've produced at the end of running your flow. And two of those things are really mature. So in the code world, lots of people have talked about using Git, for example. We can trace Git back to other tools like Subversion and CVS, going back a long way. Code version control isn't new. It's used everywhere by everyone. And if you're not, you really should be. Environment, that came a little bit later. So being able to have virtual environments, things like pipenvs or RubyEnvs, virtual machines, and now we can containerize a whole environment. You can put it into a Docker container, you can push and pull it around, and you know that given your particular hash of your environment or your particular hash of your code, you know exactly what you're running and where. Data's kind of stuck, and I do say this in the context perhaps more from the civil engineering space and geospatial systems and people pushing and pulling that kind of data around. But there's an awful lot of pushing raw files around. So we talk to people, and these are large organizations who their primary means of sharing data internally, especially in these COVID times, is via their SharePoint instance and files in folders like this. That's not uncommon. And it's been really interesting talking to people, hearing some talks, people talking about tools like DVS and there was another one recently as well, a new one that we've just heard about. We know about things like DAT, and Pachyderm is another one that I know of. And those solve subsets of the problem. And I'd love to talk a bit more about some of those particular tools, and particularly the ML space, right? They have a real particular need for being able to link the source inputs with a particular run with the output. it's version control, but it's not so much about managing the change in the data. It's about linking a particular input to a particular output. And so we've been working on this project called Kart. Kart teaches Git how to deal with tabular and spatial data. It's built on Git. So if you know how Git works, you'll be extremely comfortable working with Kart. The backend is fully compatible. So if you can host a Git repository, you can host a Kart repository. One of the other things we identified in other tools was it might not be so portable. It might only run on Windows or Linux. We built Kart for all the major systems. It's a public project, so if you visit kartproject.org, you can follow the GitHub link. You can see the code. It will be free and open forever. So perhaps the simplest thing to do is actually jump into a demo. Oops, wrong window. So I have some data. I have some river flow data from, I'll have a look in here. Two source data sets coming from MFE, Ministry of the Environment, and I want to put them into a Kart repository. So I'll make a folder called rivers, and I'll go Kart init, and that's exactly the same as Kart init. What we're actually doing is creating a Git repository, and then we're basically wrapping some things up so we can help Git to understand structured data. I would note that you can version control your raw data in Git if you wanted to, but you're versioning controlling a text representation of your data. It's not going to work for any binary data. It's not going to work for giving you a cell by cell or a row by row comparison, because the order of your data might change that isn't actually significant. That sort of thing. So I've created a new Kart repository in this folder. And just like Git, I can go, well, similar to Git, but I can go import, and I'll get that river flows data set. What this is doing is importing, let's see, we got 250,000 features, geospatial features, into this Kart repository. So if you're familiar with Git, you know that there's a working tree, which is like your working copy of the data. So that's the stuff you're looking at and working with day to day. And then there's the hidden Git repository. So this is doing two things. It's importing all my data into a Git repository, and it's creating a working copy. Now, we're working with data. So really, we want to be working with a database. In this case, we're going to create a geo package, which is sort of a spatial, a specialized spatial SQLite database. But we also support a Postgres database. We can push it to Microsoft SQL, and we're adding more support formats all the time. So there's nothing special about the geo package. There's nothing specific to the tools that I'm going to use today. We don't want to support any particular set of tools. We want to make it work for any kind of data working with any kind of system. Okay, so I've imported that data, and I'll open that in QGIS, which is a really great open source geospatial tool. I could be looking at this database using SQLite. I could be loading this into Postgres and building a web app from it. I could be loading into Postgres and running all sorts of tooling across it. So again, I'm just using this tool because it's really nice and visual, and we can demonstrate what we're doing. Okay, so we've got this data set. Let's make it a little prettier. We can symbolize on the flow. I'll zoom out of it so we can see it. All right, so we've got a data set of the entire North Island River Central Line with flow rates, and that's how fast it was to bring it into the system. Now, the classic thing you can do with Git, right, is create branches, make changes, merge branches, and deal with changes to your data set. All the same things you can do with Git, you can do here. So if I go Git branch, remove Waiheke, we're gonna remove Waiheke from this. So I'm gonna switch to Waiheke, and we'll find it here, and we'll hit edit. So if you're familiar with QGIS, this will be a familiar flow. If you're not, don't worry about it. All I'm doing is removing some records from a database. And I can go Kart status, exactly like get status. It tells me there are some changes. I can see what those changes are. If I want to look at them in a map, I can do that. I can go output HTML. It's in a local projection, so because we want to display on the map easy, I'll do it. Oops. Okay. Here's the diff of the changes that I've made. I've removed those features. I will commit that change. So again, just like it, because it is get under the hood. All right, that's done. Waihiki's gone. So just like it, I can switch branches again. So I can go switch back to main. Hit the refresh button if I can find it. And Waihiki's back. I should have chosen a more obvious layer. Let's make this really a lot more obvious. Okay. So my features are back in the map. Because I'm on the main branch, so I can switch between those branches. Kart will deal with pushing and pulling the data into the database that I'm working with. And of course, I can merge them. Okay. Refresh, it's gone. Just like it, I have a full log. So I can see that a few minutes ago, I have removed a bunch of features from this layer. I get a cryptographic hash. So at any point in time, I can uniquely identify a particular state of the data. Now, I know that this hash guarantees the state of my data at any particular time. And if I was to push this up to a repository and someone else on my team were to pull that down, as long as they have that hash, they know exactly what the state of the data is, and there's no disagreement about it. I can also push it into different data formats, right? So I could be working in my desktop GIS. I could be pushing that to someone else who is working in a different system. They're working with ArcMap, an Esri tool, or they're working with Postgres and running their own software of it. But the real point is that if you are working on this, you're trying to specify your code and your environment. Kart lets you do the same thing with your data in a non-ambiguous way that works exactly the same way as Kart. So if you as Git rather, so it's very easy to plug into those existing tools. We also handle merge conflicts. That's a little hard to demonstrate quickly, but a particular issue with dealing with spatial and tabular data is that how do you represent a merge conflict and deal with it? So Kart provides a merge conflict resolution flow. We can also talk about some of the roadmap features. We are currently working on spatial attribute filtering. So a key problem we have is that some of our data sets are very large. So at Coordinates, we host data sets like the New Zealand Linds's Cadastre. That's a weekly updated property file for the whole country that goes back a decade. We have the full version. We have the full history of that in Kart repos. But quite often you only want to work with the latest version and you only want to work with a subset of it. Well, with a combination of Git shallow clones, which lets you get just the latest version, and with spatial and attribute filtering, you can actually clone down a version of the repo that is much, much smaller, and yet it maintains the full history of the repo. So our next release will be focused on providing those sorts of features. We currently support vector formats. We will be adding support for point clouds, raster data, and grids. We're also looking at other types of formats like building information modeling data as well, so that you can do all the same version control with your vector data as you do with your point cloud and raster and grid data. We're adding more import and export formats. So we're also building on top of GDAL, the Geodata Abstraction Library. That means that we can import things like shapefiles. We can start version controlling CSVs. Again, the idea is not to force you to bend your processes and tools to our system or to Kart. The idea is that Kart comes along and you layer on top of what you're already doing to add data vision control very easily. We have another collaborator who is building a Kart plugin for QGIS, which is cool. And we're also building a desktop app, but that's a proprietary thing that's coming soon, so I won't focus on that too much. Yeah, thank you. So if we have questions, I'd love to go through them now.
Thanks so much. And yeah, indeed, we do have questions. I hope everybody can hear me okay. So the first question is from Roland Bergen, who asked, handle large data files well. Is there a maximum you can handle? It can handle, for example, like 0.5 terabyte FASTQ files or genomics, because Git used to work really poorly when Roland and his colleagues were his colleagues were trying to use it for big data sets.
Yeah, I mean. So for context, some of the largest repositories we have are, like I mentioned, the LINS property cadastral files, which are, 500,000 features with weekly updates going back 10 years. I forget exactly how big it is, but it does approach the sort of 100 gigabyte type mark in total. There's no actual limit, and we've benefited greatly from the likes of Microsoft, who have done a lot of work to make Git scale up to very large repositories. One of the reasons that Git doesn't work great for large data sets at the moment is that the hosting around Git is generally geared towards text files and a smaller number of text files, whereas the way we use Kart and the way you optimize the backend involves lots and lots of small files. So there is a lot of tuning that you can do to improve the performance. Whether we can go quite that big, I don't know. But we are working with some significantly sized data sets, and this one of our benefits in our position hosting the data we do is we've been able to really stress test it against some very large data sets with a lot of history.
Thank you. We do have 2 more questions and some more time to answer them. So Maxime is asking, is there any plan to support other structured data formats like NetCDF or HDF?
Yes, absolutely. So I mentioned at the end that, on our roadmap, we're looking at point clouds, raster, and grid data. Those are slightly higher up the roadmap at the moment. I would note it is an open source project. If someone would like to, we would love to have people come along and add support for the formats they would like to support. HD5 would be a really great one as well. Yeah, the idea of having detailed version control of NetCDF would be wonderful.
Thank you. And then Eric has a question that I think also something that I wanted to ask. So it looks like Eric says Kart uses Git heavily behind the scenes. So would it be possible to alias Git for Kart and not have to remember using a different tool? Or alternatively, could you have Kart as a command?
So the answer to the first question is probably simpler. Kart, it's built on Git. It does still support file trees under the hood. And an example of where that actually happens is we support metadata. In fact, I should show that because I can. Oh, it won't be in this one. Ah, yes. So we support full XML metadata, for example, that comes from our clients, and license files, for example, are already in there. So file working trees do exist in the background. We just haven't got around to building the changes we need to make to expose that to the actual working tree so that you can actually work with it. It's on the roadmap on the website, but the idea that you should be able to version control your data with your code at the same time, and any other artifacts you want to include, it will happen eventually. Whether you can alias Kart to Git is that, or a subcommand in Git, unlikely. So we are working to get some extensions into Git the upstream project, particularly around the spatial filtering. So we want to have sort of hooks so that we can add more and smarter filtering into Git, but that requires getting buy-in from a very large and diverse open source project with different priorities and things. So having it as a sub-command of Git probably isn't on the cards.
Thank you very much, and thank you for your talk. And we have our final presentation for this session. Mike Laverick from the Center for E-Research at the University of Auckland is going to be talking about automating instrument data workflows, integrating Globus into MyTardis. Mike, over to you.
Kia koutou, everyone. Hopefully you can all hear me okay. So yeah, my name's Mike Laverick. I work at the Centre for E-Research at the University of Auckland, and I'm going to talk to you for the next 15 minutes about how we've been automating some instrument data workflows at the university, in particular using Globus and MyTardis. So as I said, I'm going to talk to you about these two tools. I'll first briefly cover the needs of scientific instrument data nowadays, the issues surrounding merging these two tools together, how we address these and create a proof of concept, and then going forth, how we're going to productionize and how we're going to make some future developments. So of course, it's probably no need to tell most of you here, but research instruments are always improving. They're getting larger and larger, and they're generating bigger and bigger data sets, gigabytes, terabytes. Some of the new instruments that we're going to get are probably going to be producing a terabyte or two every week. So you can imagine if you've got 10 of these instruments, it's going to take up a lot of storage. Of course, as the instruments get bigger and bigger, so does the processing of this data. Pre and post-processing pipelines are more and more sophisticated, and they even require HPC nowadays before you have a science-ready data set. Of course, we're doing science and research. Everything should be reproducible, and that means capturing all of the experimental conditions and processing conditions in machine-readable metadata so that we can have all of that information in the future. And there's a growing need to share all of this data with collaborators that may be around the world. We're all on Zoom. We all know things are going digital and borders are breaking down. So onto the two tools that I mentioned that we're going to be using to address these problems. The first one is MyTardis. Now this deals with metadata, storage, and data access. In essence, it is a metadata and access control database in addition to a web portal. It has a hierarchical data structure where you have experiments. Within those experiments, you produce different data sets. And of course, each of these data sets have data files associated with it. MyTardis lets you create schemas, so you can define structured metadata at every single level. So you can have metadata for the data files telling you how they were produced individually, and you can have metadata all the way up to the experiment level to tell you some overall parameters associated with the entire experiment. MyTardis connects with a load of different storage backends. It connects with local storage, network drives for universities, cloud storage, etc. And one of the key things is that it has top-level access controls. So you can define who can access these experiments and to what degree they can access them, be them individual users, be they research groups, or even the public. So one reason we've been using this is because it's an open source Python Django code base, and we've been doing some active developing of it at the University of Auckland. There's a lovely list here of things that we've been working on. We've actually been changing the access controls so they sit at every single level. So what you can do is you can control right down to the individual data file, who can access it and to what degree, for lots of flexibility for the researchers. We've introduced new permissions. So we've separated read and download. So in some cases, you can only read the file, other cases you can download it. And we've even introduced a sensitive flag into it so that you can restrict some metadata from the public and even from other researchers and limit it right down to a couple of key admins. We envision this for things such as medical data where we've got sensitive information there. We've added a new hierarchy level just to make it even more scaled down. We're introducing persistent research activity identifiers, or RAIDs. And the key feature that we're particularly proud of is we've now introduced a big search capability on all the metadata in the database. So if you can tune your query just right, you can pick out one file from millions just by querying for the specific metadata that you want. It's a pretty powerful tool, and we're developing it quite a lot. I'll stop talking about this because I can talk about it forever. The other tool to solve the other problem that we're using is Globus. Probably quite a few of you have heard of this. It is a transfer service that you can use to transfer large data sets at high speed and securely. The data sets transfer directly from an endpoint to an endpoint. There's no intermediate servers, so you can send it directly from your machine to the destination machine that you want. You can set up personal endpoints, for instance, on your own laptop or university or institute's machines. And there's also institutional server endpoints that you can send it to, such as HPC infrastructure like NZRSE or universities. And you can also create subsets called guest collections that you can share with other collaborators and users. In terms of developers, Globus integrates with almost every storage backend that I know of, all the way from tape archives all the way through to cloud storage. It has a great command line interface for you to use. There's web APIs, and in particular, there's a software development kit, which is for Python. In summary, if you're moving research data, use Globus. Some of the networks that Globus goes through can be as fast as 100 to 200 gigabyte connections. It's pretty cool. So those are the tools, but what are we actually using them for? So I'll go through an example workflow that we have for one of our instruments. The instrument generates some raw data. Let's say it generates about a terabyte of images. The instrument then has some codes on it, so we can generate some metadata and access controls to decide who can access this data and capture all of those key parameters. All of this information is then fired across and ingested into the MyTardis database. The raw data goes to centralized storage. The metadata and ACLs go to their specific databases. And great, we've got some basic information about these. But now, if you actually want to use this raw data, sometimes it needs to go to NZRSE for some pre-processing to actually make a science-ready product. So now the user's got to take it from MyTardis, transfer it to NZRSE. Then, of course, we want to take that back and put the science-ready product in MyTardis. So they need to move it back from NZRSE to MyTardis, in addition to metadata around the actual processing. So we have this loop back to MyTardis. And then finally, if someone wants to actually use the data, they then need to move it to analysis. So once again, the user or users, researchers have to pick up and transfer that data across to their own machines, virtual machines, back to NZRSE even, to other collaborators or to the public for the actual analysis. Now, you can notice the user's got to do a lot of steps here. And as it currently is, the user's actually got to do the intermediate transfer from MyTardis to themselves, then to NZRSE. And if you're transferring terabytes of data, this takes time. So what we want to do by integrating MyTardis and Globus together is simplify some of these connections so that we can have an instrument generate data, generate metadata, automatically have the data sent to MyTardis, the centralized storage, automatically sent to NZRSE, activate some processing scripts, bring the data back along with all of that metadata, and store it all back in MyTardis. And then we want the user, with a click of a button, to be able to request their data goes directly to one machine. So we want to cut out all of these intermediate transfer steps and streamline the process. That's simple. You just combine MyTardis and Globus. Done. But of course, I wouldn't have a talk if there wasn't some tricks about this. And there's a couple of fundamental issues with integrating these two together. Those are that Globus is designed to work with any file system permissions. It's super flexible in that way. And transfers are driven by a user via the Globus UI or CLI. So they can log onto the web portal and they can look at their endpoints and they can pick up a file and transfer it to another endpoint super easily. The problem we have is that MyTardis is essentially a metadata and access control database that replaces those file system permissions, meaning Globus can't easily pick up and know who can access what. The other issue we have is that MyTardis needs to know about the transfer activity. If we want to make sure the metadata's captured right, then we can't just have a user throwing data in it via some other mechanism. So what we want is MyTardis should be driving the transfers itself. So there's a lot of complicated reasons. I'm not going to go into them, but it's pretty tricky to replicate MyTardis access and permissions at a file system level for Globus to inherit it. There's a few workarounds. We brainstormed it for quite a while. They weren't nice. They're feasible, but not nice. So now we come on to the section where I couldn't find a good enough stock image for software development kits. So instead, I made a meme to explain the problem. The Globus SDK comes to the rescue and can fix these integration issues. So with the Globus SDK, what you can do is you can register an application with Globus. This allows the application to authenticate as itself on its own behalf, as if it was a service account. So we can set up a MyTardis service account, and this can do things by itself. Just like any other user, if you give the service account access to a guest collection, to a shared endpoint, then the service account can transfer to and from that endpoint like any other user. Great. The Python software development kit controls the service account, and by integrating the Python SDK into the Python-based MyTardis code, you can actually have MyTardis control the service account and thus control all of the transfers that are going from the data storage endpoint to anywhere else in the world. So in essence, the service account acts as a trusted agent that performs all of the transfers from our data store to any remote endpoint, be it NZRSE, be it external ones for researchers and collaborators elsewhere in the world. We can have this service account drive all of these transfers. The advantage of this is that it also means that all of the endpoints remain opaque to any of the other parties. The MyTardis user account can't see into all of your endpoints, only the bot can. And NZRSE users and external researchers can't go looking in the data store directly. All of it needs to be done through the MyTardis web portal, which is what we wanted. Hoorah. So we came up with a proof of concept. MyTardis creates an internal transfer job. This is in the form of a Django model instance, which is essentially just an entry in a database that has a job that says, these files need to be transferred to this endpoint, and it was initiated by this user. All of these pended jobs then get submitted asynchronously to Globus periodically. We have a message queue system with some built-in resilience for restarting. And this goes through and periodically submits the jobs to Globus, which will then pick up the jobs when it can. In addition to this periodic submission, we can do a periodic check of the transfer status to see if any of the active transfers have actually finished or if they failed, and pull some information back on that. So now we have a way that MyTardis can asynchronously have jobs requested, submitted, and bring back information. So the final manual tweaky bit that we need to do here is that for you to share with the service account, you need to create a guest collection on a remote endpoint and share it with the service account. If the service account doesn't have permission to write into your endpoint, it can't transfer. The other thing we need to do is to register that guest collection in MyTardis. Just because the service account has permission to go to your endpoint doesn't mean it knows the address of your endpoint. Please tell us that, and then the service account knows where it can move data to. And finally, the remote endpoints in MyTardis are associated with users and groups, and also with the project experiment hierarchy. This means we can restrict which users can move data to which remote endpoints. You don't want anyone just transferring terabytes of data into your machine. And likewise, we can restrict where some of the data, so be it medical data, you can restrict which machines it goes onto. You don't want medical data just going to any old machine in the world. So to date, we've managed to do some successful transfers from a dummy data store to a remote endpoint, to remote endpoints, and we've driven all of this using MyTardis. We've transferred to Nectar VMs, which is cloud compute, and also to NZRSE. Hurrah, we've managed to do all of the goals that we're hoping to. We've developed and tested transfer job APIs to run this as well. So these can interact with the web front end and potentially also with other trusted API access places. And we've just about finished a download cart for easier selection of the data and to submit transfers. Anyone who's done online shopping knows how a cart works. You load it up and then you go to the checkout and you transfer your data wherever you're allowed to. So what's the roadmap to production and beyond? turns out we actually need to finalize our backend storage technology. We're moving from S3 to Manila. And so we still need to do that and then set up a Globus endpoint around it. And then we'll have full access for MyTardis to start transferring this data. Afterwards, we will be helping to set up some of these instruments with automatic transfer job submissions. So when the data gets produced, we'll help them set up scripts that can use those APIs to request that the data gets transferred to, from MyTardis to NZRSE, etc. And then the real gem that we want to do is to expand out this functionality to include FuncX for workflow automation. So for those of you that don't know, FuncX is like Globus, but instead of just transferring data, you can actually request that an endpoint executes an arbitrary function on that endpoint. So this will allow you to transfer your data using Globus and then request some processing gets done via FuncX. And then finally, we want to develop out some APIs and UIs so that you can get some job status history and transfer history in MyTardis. At the minute, this information's only available to the service account and the transferer, so we want to bring that back to the researchers. So that just about wraps up my talk. So I want to say a big thanks to the rest of the MyTardis team at the University of Auckland, who you can see here, and also a thanks to Monash University, who've been developing and maintaining the MyTardis code base for the past 10 years. And of course, to NZRSE with all the help with Globus, in particular, Chris Scott, who I think is watching right now, hopefully. Thanks for the help. And yeah, I'll wrap up there.
Excellent. Thank you very much for your presentation. And we have some questions in our Q&A. So Roland Mosbergen is asking, could MyTardis act as a research data registry for an entire institute? So can it scale up?
Yes. So for some context, Monash have been using MyTardis for 10 years or so with the Australian synchrotron. They've got petabytes and petabytes worth of data in there. I think they've got 10 million plus data files in there. Yes, it can be used for whole research institutes. And we're actually working at onboarding some of the university institutes and research groups at the minute, including collections of instruments to bring on board. So yes, definitely.
Mm-hmm. Thank you. And I actually wanted to ask, is it possible to use the infrastructure that you're building with personal endpoints on Globus? So, you know, you can set up a personal endpoint on a personal computer. It doesn't have to be institutional endpoint. So would that be something that can be used?
Yes. So here's the real magic of it all. Everything we've developed so far runs on personal endpoints. So the University of Auckland has its own institutional one. They're not trivial to set up, and they require that you've got a full file storage system with all of the access controls behind it. For the use case of MyTardis, which was the file system permission database in front of it all, it was going to be quite tricky. So yeah, we used a personal endpoint instead. And yeah, it can fire to any endpoint anywhere. There's no restrictions there, so long as you can set up a guest collection to share with it, which I think requires a plus subscription on Globus, but at least for the researchers in New Zealand, NZRSE has kindly got one of them for everyone.
Correct. Yeah. Yeah, that's why I was asking. Thank you so much. Big thanks to all our presenters, and thanks everyone for attending this session. Namihi. And now we're going to take a short break until 11:15, so 11:15, when our next session on HPC and code optimization, part 2, after part 1 yesterday, will start. So see you everyone at 11:15.